Hi, everyone. Welcome to the trainee sessions. It is my pleasure to begin with Davor Kuric. I hope I pronounced your name correctly.
But you're very close.
Yeah. He will present deconstructing scale-free neuronal avalanches during behavior. Take it away, Davor.
All right. Hi, everyone. My name is Davor from the University of Calgary. And today I'll be telling you about deconstructing scale-free neuronal avalanches during behavior. So we all know that the brain is this highly efficient information processing machine. And one of the mechanisms that enables this, or alternatively is a byproduct of this efficiency, is what physicists like to call the critical brain hypothesis. Now, all this really is just the observation that neurons in a resting state brain, in electrophysiology, fMRI, and anything in between, tends to exhibit scale-free information cascades, which we also often call neuronal avalanches. So some examples are here. Now, what I mean by scale-free is simply that on this log-log plot, it follows this straight line behavior with some characteristic slope, and in fact, often it is 1.5. And this scale freeness has been tied to efficiency and information processing. And it's really the slope here that gives us a lot of clues about what the underlying dynamics are. And so it's for this reason that it's become a really popular tool or method that physicists use to analyze collective neural population activity. However, whether or not this criticality and by extension optimality persists during behavior is actually still an open question and kind of the main topic that I want to talk to you today about.
Seem to have lost a bit of the connection. Okay. We'll try to bring the speaker on. Davor, are you still online? Can you hear? Okay, you can hear me. I'm just going to bring you back to the screen. And if you can share your slides again. Okay. Yeah, trying that again. Are you using Google Chrome? Okay, so there was a camera disconnection. Hopefully you can connect back on. Yeah, I'm trying. I will try one more time. Hello?
Oh,
we can hear you, but we don't see your screen.
that's weird. It looks like my camera somehow died.
Can you share your screen? Are you able to do that?
I don't see the prompt for it anymore.
Okay. Can you put the link to your Google Doc on the chat?
Yeah. Oh, I'm not sure how to do that. I've never done. Oh, share.
Yeah, if you can copy it. Okay. Okay. Do you see my screen? Oh, it's a bit complicated because I need to request access. Okay, I think we're going to need to move on to the next speaker, and then we can try again at the end of the session if it's possible to repair the camera, okay? Okay. Okay, everybody. So we are moving on to the next speaker. And if you would like to share the screen, just like before, just like we practiced, yeah.
Should be this one.
Perfect. Here we go.
So should I start it?
Yeah, take it away.
All right, so hi everybody, my name is Kunan Nguyen, and I'm excited to be here today to talk about my postdoc work with Dr. Rubczynski at IUPUI. So synchronization is a common phenomenon in the brain, and oftentimes collective neuronal behavior is established through synchrony, and abnormal synchronization is associated with many neuronal disease. So in experiment, it's observed that synchrony is not constant throughout the entire time, but rather is fluctuate over time. So the system can come in and out of synchronization often, but for in a random manner. So therefore, the temporal pattern of synchronization is an important physiology feature that we want to study using computational model. So here is a schematic of our model. On the left, you see our model is composed of two small circuits, circuit 1 and 2. In each circuit, we have two excitatory neuron and two inhibitory neuron connected to each other by various synaptic connection. And with parameter tuning, we tune the network to operate in the gamma rhythm band, and using technique that has been developed and used in previous experimental study and computational study, we define when the signal synchronized or when the signal desynchronized, and the number of consecutive cycles in which the signals are synchronized, are not synchronized, is defined at the duration of desynchronization. So here on the right, I show example of the synchronization distribution. On the top is duration of the synchronization from experimental data of autism patient obtained from EEG recording, and on the bottom is the synchronization duration from our simulated model. And as you see from both histogram, the mode of the distribution is 1. That means most of the time, the duration of the synchronization duration lasts for like 1 cycle. So it's short. And it's in fact is a common things that is observed in experiment. So now with our model, we would want to study what kind of factor that can alternate synchrony pattern. So one thing that we look at is synaptic connection between the neurons. And we decided to look at synaptic connection because the synaptic connection between E to I and I to E neurons are important in establishing the gamma rhythm, and also abnormality in E to I and I to E balance or connection has been observed in many patients with autism or epilepsy. So with that in mind, we look at the local connection, the excitatory local connection GEI shown on the left. As we increase the value of GEI, we see that the distribution of the synchronization changes. It's go from like mode 3 as shown in this example to mode 1 when GEI is bigger. We also look at excitatory connection across circuit, so the distant connection. And as we increase the value of CEI, we see that the distribution changes from mode 1 to mode 3 as shown in this example. When CEI is small, we have mode 1. And when CEI is bigger, we have higher mode, so mode 3. So we say that a large value of local excitatory connection tend to produce short desynchronization, while large value of distant excitatory connection tend to produce long desynchronization. And in addition to excitatory connection, we also look at inhibitory connection, so like I to I and then I to E connection. And we see that in those cases, synaptic connection also change the synchronization pattern over time. Moreover, as I mentioned earlier, system with similar synchrony strength can have different synchrony pattern, and is observed in experiment, and it's also been suggested that synchrony pattern can be a better measure instead of synchrony strength in order to detect the difference between a healthy subject and disease subject. So with that in mind, in our computational model, we want to create a scenario in which the synchrony strength and the firing frequency stay the same as shown here, but the synchrony pattern, so the desynchronization distribution is different. So in this case, when K is small, we in the regime of long desynchronization. As you see, the mode of that distribution is 3 when K equals to 2. Now, as you increase K, we go to a different regime. And in this case, the system produce short desynchronization duration. And as K getting bigger, the distribution become even more short because the mode is even more prominent. So with this example, we show that desynchronization pattern can vary independently of synchrony strength and frequency. So with the small model, so our model is small, we've seen some encouraging result in the case, in the sense that most of the mode of the duration is 1, which is consistent with what we see from experiment. We also seeing that synaptic connection play a role in affecting the temporal pattern of synchronization. And now we're working on extending to a bigger network so that we can look at population synaptic field. So like similar to the idea of LFP in experimental study. In order to investigate synchronization. And with that, we can look at many more factors such as network size, or like network structure, connection strength, and connective connectivity probability, and see how they change the synchrony pattern, which in turn how that can affect the functional implication with different synchrony patterns. Right. Thank you. Do you have any questions?
Thank you so much for the talk. I don't see any questions posted here. So I was wondering, what your plans are for applying this model experimentally. Oh, and we do have a question that's coming up.
So the plan right now is still working on the bigger model, like bigger network, and see how the synchrony pattern can have an effect on different functional implication of the network. So like how the network encode information or how the network synchronize. So how the synchrony pattern can affect the synchronizability of the network. And we don't have any experimental data, but the synchronizability ability can, in fact, inform us of the difference between healthy subject and disease subject, because they can have like different functional ability.
Yeah. Okay, great. And you're focusing on autism.
Yeah. Yeah, we want to have
yeah.
like how the model can be applied to data from like autism patients.
Sounds good. We have another question. Do you plan on perhaps looking at how conductance delays between neurons affect a neural synchrony?
Yes, we do. That's actually one of the things we've been talking about. So, yes.
Okay, thank you very much. Any other follow-up questions? Okay, great. So I will invite Davor to the screen. Try this one more time. Okay, thank you so much for your talk.
Yeah, thank you.
Sorry for cutting you off there. Hi, Davor. You want to try it again?
Sure. From a new view. Sorry again about whatever happened.
Okay, great. So you're sharing the screen and okay, perfect.
Awesome.
Take it away.
All right, once more. All right, hello everyone. My name is Davor Kurik from the University of Calgary, and I'll be telling you about deconstructing scale-free neuronal avalanches during behavior. Now, we all know that the brain is this highly efficient information processing machine, and one of the mechanisms which enables this, or alternatively is enabled by this, is what physicists call the critical brain hypothesis. And this is simply the observation that neurons in the resting state brain, when measured by either electrophysiology or fMRI and scales in between, often exhibit scale-free information cascades, which we call neuronal avalanches. And what I mean by scale-free is simply that on a log-log plot such as this, various statistics of these neuronal avalanches will follow this straight line behavior with a characteristic slope typically seen around 1.5. And there's been a lot of research into tying this scale-free property with information efficiency. But it's really the slope here that gives us a lot of clues about the underlying dynamics, and has been really kind of become a popular tool for physicists to study collective neural behavior. However, whether or not this criticality persists during behavior really is still kind of an open question. And that's really what I want to talk to you guys about today. And the context in which we will be doing it is extremely simple. It's just a mouse that's able to run or not of its own volition on this non-powered track. It's 2-photon calcium imaging in the retrosplenial cortex at this kind of single cell resolution that you can see here. Now, I believe one of the reasons why establishing criticality during behavior is such a difficult thing is because we often tend to neglect a very key aspect about neurons, and that is that even within a small localized population of neurons such as this, we will have neurons whose response to stimuli or behavior in this case is highly diverse. So as an example of this, we're looking at neurons from our experiment here. And we're just looking at the signal averaged onto all transitions between the standing state and the running state. And what you can see is that there's neurons here that are, in this transition, are upregulated in their activity, but there's also neurons who are downregulated in their activity as well. And I should really emphasize here, this isn't just a manifestation of me just ordering these in this way. These classifications of up and downregulated persist from recording to recording and are really robust. So one can then ask, how are these dynamical subsets reflected at the total population avalanche statistics? And that's exactly what we're going to look at. Let's define the downregulated group as just the subset of cells suppressing their activity. The upregulated group is just the subset of cells increasing their activity. And now what we can do is compare avalanches on these subnetworks against the total population statistics and see how they're reflected in one another. So let's do that. But first, let's look at what we see when we just look at the total population statistics. So when we completely disregard behavior and we're looking at the total population, we get what we call these unconditional avalanche sizes, and they follow this kind of characteristic straight line behavior with a slope of 1.8. However, when we condition the avalanches as having occurred during the standing state or the running state, so that's red and blue curves here respectively, we see that this actually decomposes into two very different statistics for the standing state and running state, and the two different slopes as well, so 1.5 and roughly 2.5. And here, the shallower slope, all it really tells us is that it implies that larger avalanches are more likely when the animal is running. So large avalanches actually give us the information about the state of the animal. So we also see that the slope depends on the behavior, and that when we disregard the behavior, we actually generate effective statistics with an effective slope here. All right, so now let's look at what happens when we kind of split it off into these down-regulated and up-regulated groups. We see something interesting, and that is that the unconditional statistics of these subgroups resemble the conditional statistics of the total population, by which I mean that when we look at the total population conditioned on behavior from the previous slide, we see that the up-regulated group has very similar statistics to the total population in the running state, whereas the down-regulated group is for the total population in the standing state. They have very similar slopes, as you can see here. Of course, one kind of conceptual model that you might think of right away is kind of a switching between two dynamical regimes, and we can actually test for this and ultimately rule it out simply by conditioning these subgroups onto behavior. So let's do that. And what we see is that when the animal is standing, so that's the red distribution, we have the same statistics in every case. So 2.5 and 2.5 roughly on both up and down here, which is exactly what we see at the total population level. However, it's when the animal transitions into the running state, so the blue distributions where we see the differences. We see that the down-regulated group has a slope of 3, whereas the up-regulated group has a slope of 1.5, which is what we see at, or close to it, which is what we see at the total population level. So it's less of a dynamical switching between two regimes and more like one subgroup is dominating the statistics. Kind of put this reverse. The total population statistics that we love looking at may not always be reflective of every dynamical sub-ensemble of our population. So really what this is kind of saying is that just like we saw when we neglected behavior, we mixed our different avalanches to create kind of effective slopes. What we're seeing here is that the ignorance of the real underlying network, whether that be functional or structural, leads to mixing of neuronal populations with different dynamics, effectively giving us different slopes, which may then imply different underlying dynamics. And this really kind of leads us to call for maybe like a reinterpretation of how we handle criticality during behavior, keeping in mind these different dynamical subgroups. So with that, I'll just end it off here. If you want to follow up with anything, more questions, my contact information is down here. And thank you to my collaborators and for the hosts of this, for letting me present. Thank you very much.
Thank you so much for your talk. Just before a question is entered here, I was wondering, in what do you think would be a functionality of these dynamic switching at the behavioral level, or let's say in the context of perception?
That's kind of where we're a little bit limited in the fact that we're looking at specifically the retrosplenial cortex in this case, because the retrosplenial cortex is kind of often viewed as potentially a hub between the hippocampus and kind of higher or order areas of the brain. And so one of the functional reasons that we thought maybe is occurring why we have this downregulated and upregulated group is that it really is kind of serving as a hub that's kind of directing information from one area to the other. How this would change in different areas is something that I'm really interested in. Would it be that one group really dominates the other group at the total level? Maybe, but we're not entirely sure without actually going to look at these other areas as well. Hopefully that answers your question. Maybe I misinterpreted it. Yeah,
that's great. Thank you so much. Thank you for your talk. And I'll now set up for our third speaker.
Thank you, everyone.
Okay. Okay, there is another question. For the same time bin, the exponent should depend on the firing rate. Could your results be explained by a change in rate? Davor, do you think you could answer in the chat? Okay, Hussein, let's share the screen if you're able to.
Hi, thank you for letting me join. My apologies for the Wi-Fi issues.
No worries.
May I begin?
You now? Yes.
Hi. Okay.
Please go ahead.
Hello, everyone. Thank you for letting me in. Thank you for having me talk. My name is Hussein Ather. I'm a PhD student under John Griffiths here at the Kremble Center for Neuroinformatics. This presentation is about my project, Deep Learning-Based Parameter Estimation for Neurophysiological Models. In computational neuroscience, there's been an emerging paradigm of connectome-based neural mass models, or CNMMs, used for measuring large-scale mesoscopic activity in large patches of tissue to measure regional neural activity. Typically, we use CNMMs as computational graphs, and we can describe a sequence of numerical operations as input-output relationships along all the steps of some sort of computational process. This lets us use CNMMs as models of systems of equations that depend on various parameters for measuring neuronal activity. However, figuring out which parameters and parameter values are the best to use can be very computationally expensive and time-intensive due to the number of parameters in the wide parameter space region. For this reason, in this project, we introduced a novel approach to parameter estimation. This novel approach uses deep learning tools from the PyTorch optimization framework in Python. We also use a modeling and model fitting framework of taking input fMRI data, typically time series data, as shown here on the left, of functional connectivity or structural connectivity, with these matrices of true functional or true structural connectivity values, of time series data, which measures the correlation values between brain regions or parcels of the brain. And by taking this input data and inputting it into a loss function after using it with a model for various parameters, we calculate the gradient of the loss function itself as we change various parameters of the model. The loss function itself exists to maximize the entropy given by the model itself. So the loss function gives us a value for us to maximize for the various parameters of the model. And by using the atom optimization algorithm, we can use the gradient values calculated from the various loss functions in figuring out which parameter values are the best to use. From this, we can figure out which parameter values are the best for a given model, given input data. For this project, we focus on the reduced Wang-Wang-Deco, or the dynamic mean field model. The Wang-Wang-Deco model approximates the average neuronal ensemble behavior for a group of neurons. You can describe the activity using state variables, excitatory and inhibitory potential, representing synaptic activity levels, as well as auxiliary variables, such as the population firing rate given by R, the gamma kinetic parameter, tau for the time decay rate constant, and sigma nu for the Gaussian white noise parameter. Given together, we can use these systems of equations as parameters that can be optimized. By converting the input currents to firing rates using these final two equations here with the sigmoidal linear tanh function, we can then introduce our own variables, GIE, GEI, and G to substitute for the synaptic coupling strength parameters, J, as well as to substitute them in for these global scaling factors, local scaling factor, W plus, and global scaling factor, capital G. And we can introduce these parameters and optimize these four parameters on the right in figuring out which parameter values are the best to use. This gives us a way of simplifying things a bit and giving us a way of looking at four specific variables that are interrelated to one another that can be optimized during this parameter optimization approach. Interestingly, the Wang-Wang-Zecco model is one of the few widely used neural mass models that's directly derived. It's directly derived using mean field reduction techniques based leaky integrate and fire neurons themselves. By using some synthetic data or synthetic data with some true values that we know about, we know the true values, and we can just use then we can just adjust the parameters accordingly to figure out which parameters are the best. The error distributions shown on the left show peaks of the relative error for the four parameters centered on 0 with strong peaks values with relatively low or small widths. This shows that the majority of the fits accurately do recover the true correct parameter value. Similarly, we can observe the corresponding structural connectivity matrices and functional connectivity matrices on the right. Initial SC values show the structural connectivity matrices generated with random initial parameters, and modified ones show the SC matrices given by the model fitting results themselves. Each row represents a different method of calculating the structural connectivity, shown here on the left. Take note of the secondary diagonal, because that's very important that our model fitting methodology and model fitting results can actually show us what the secondary diagonals look like. Many times in these methods of measuring structural and functional connectivity, it can be hard to recover that. Comparing this to the simulated functional connectivity, we have a way of creating both structural and functional connectivity values from the model fitting results themselves, with the optimal parameters. Similarly, on some experimental empirical fMRI data, we can show what the default mode network structures look like between simulated functional connectivity and empirical functional connectivity. So basically using a seed region to see what regions of the brain might be highlighted and what regions of the brain are activated, showing that there's a strong correlation with the posterior cingulate cortex in the superior frontal region and the precuneus region. Similarly, we can also take a look at the empirical and modified structural connectivity matrices and compare them to the empirical and simulated functional connectivity matrices. So these experimental data results are from the Human Connectome project, the HCP results. The typical values for these types of fits are comparable in the CNMM modeling studies with fits of R to 0.3 to 0.5, and there's a much more nuanced contrast after the optimization. This is further shown in the actual data fitting results of the parameters themselves. Comparing the orange and blue lines, so empirical and simulated functional connectivity values, we have good fits, relatively good fits for 3 of them. These data fitting results show that our optimization approach works pretty well on empirical data. And there's a much more nuanced contrast after the parameter optimization itself. In conclusion, we were able to develop a novel deep learning-based parameter estimation technique for these neurophysiological models. We also showed that there was a robust recovery of the physiological model parameters in synthetic data, which was then applied to experimental resting data from MRI data. From there, we can use some future work to generalize and figure out how the model fitting method can be used in other models of neural dynamics, task-evoked activity, and non-fMRI measurement types. This wouldn't have been possible without these people and these institutions. Thank you.
Great. Thank you so much, Hussein, for a very interesting presentation and novel method. What data sets have you applied,
We've applied
it to
a
so
few.
far?
I mentioned the Human Connectome project data sets. So that's the known data, or well, that's the experimentally derived data. The synthetic data was from the Hogman et al. 2008 fMRI 66x66 set of brain regions, the brain parcel. So that's the known data, the synthetic data. From there, that was how we were able to figure out which parameter values were used as the true values, because those are the ones we Those are the ones directly taken from the data itself. So someone had a question. Oh, that's not for me.
Mm-hmm.
That's not for my presentation. Okay.
No, it's from the previous one. Maybe until more questions are added here. So I was wondering, so if you simulate data from the model, how robust is the method? How robust is your method in terms of parameter estimation when you apply or inject different levels of noise? Is there at some point where the parameters can no longer be recovered?
That's a good question. I think that's an interesting that could be an interesting point of further research. I guess I would want to look at how noise would vary with different sets of data themselves, because I could imagine that the Gaussian noise necessary, the Gaussian parameters, as I mentioned. I think I'm still sharing the screen. You guys can remember in the variables, the Gaussian parameters are the sigma nu.
Mm-hmm.
Yeah, right. I anticipate the variation probably wouldn't be too significant, as we're only adjusting these 4 parameters shown down here. However, we just set it to center the mean at 0 and some rather arbitrary value of variation. Probably, I think we just use 1. We just use 1 for the variance. So.
Okay, there's a question from Francis Skinner. You said that the fit was good, but it was a bit quick for me to see. How was the goodness of fit evaluated?
Right. So my apologies for not showing the goodness of fit histograms, but we did just make some scatter plots of the structural connectivity and functional connectivity matrices against each other, as well as the scatter plots for fitting results of empirical and functional connectivity matrices against each other. I could just quickly share a new tab and show the data itself, but I'm assuming just taking my word for it would be sufficient. With the R values, with the R values wouldn't actually tell you what you're looking for there, but there was a general linear trend between them. So yeah, just empirical scatter plots. Can you give more info on the structure of the deep nets, the validation and error bars, and the parameters? Right. So the deep neural network, deep neural network was pretty. Right. So the deep neural network itself, it was just generally from a code functional point of view, like creating these classes and creating models of the classes themselves using the PyTorch model, using the PyTorch model functionality, and setting the tensor. Sorry, we tested that with PyTorch and with TensorFlow with similar or same results that showed like very, very good fits themselves, and essentially just taking some sets of framework used in model fitting approaches and other sets of data in other contexts, and saying that the connectome-based neural mass models of the Wang-Deco do follow a similar set of equation that can be used. Same statistics of population firing rates, of the synaptic coupling strength variables, such that we could apply the framework the same way there. So on the validation and the error bars for the parameters themselves, essentially the error bars for the parameters themselves, or rather the error for the parameters themselves, is given by the relative error in the histograms here, with some just very, very small widths with a slightly big width for the GEE parameter. Yeah, essentially when you're creating a deep net, you do just want to generally the best thing to do is to figure out like what exactly it is that you want to optimize, and what exactly it is that you want to optimize. And by looking at various sets of data themselves and just changing some sets of parameters, or perhaps looking at things a priori themselves, like it wouldn't really do as much good to change sort of like input currents based off of time series data for the Wang-Deco model of the functional connectivity strengths themselves, or it wouldn't really do us that much of a good to change some of the other parameters themselves. And essentially, these coupling strength parameters would change drastically based off of different sets of data. And that's what us researchers are interested in finding out. So we center the deep net around those parameters.
Okay, thank you so much. If there are no further questions, I will end the session by thanking again the trainees excellent talks today and thanking you for your attention.
Sorry, it looks like someone asked another question. Davor.
Oh.
It's a good, I don't know the answer from a quantitative point of view. One thing I could try, which I has not of yet, is making the time bidding smaller in the running state. Oh, right, making the time bidding larger. Yeah, that would be making the time bidding larger. Yeah, absolutely. Right. Oh, right. Yeah. For the various batches and for the processes themselves. That's a good suggestion too. We were messing around with how long each epoch would take. We only have right. Oh, okay. Yeah. Yeah.
All right. Thank you again. Thank you again for your talk, Hussein. And thank you everyone for your attention. And just to remind you, tomorrow we start with Trainee Spotlight at 9 a.m. And then at 9:20, we have additional parallel trainee sessions. Thank you so much, everyone, for a great first conference day. Have a great evening and see you tomorrow. Bye.